I welcome to our project beyond inductive graph matrix completion for CS6101. Recommendation systems, as you might all be aware of, have really great potential applications to commercial use cases. They are frequently used to recommend interesting content for users in e-commerce and social media websites, such as Netflix, Spotify, and Shopee. In particular, matrix factorization is currently one of the most widely used techniques to build a recommender system. However, matrix factorization is intrinsically constructive, meaning that the model is unable to generalize to unseen users or items during training. That's a really big deal, because this causes both scalability and transferability issues, which may seriously impact business demands. Luckily, recent developments in graph neural network models, GNN models, have allowed for state-of-the-art performing novel architectures that incorporate both transductive as well as inductive learning methods for recommendations. One such inductive method is the focus of our project, Inductive Graph Matrix Completion, IGMC. IGMC is a state-of-the-art inductive model to predict ratings in the setting of only having ratings of each user-item interaction. That is, without any additional user or item set information. We extend this model by introducing other successful architectural developments in GNNs, such as graph norm and layer aggregation methods. Furthermore, we explore the transfer learning capabilities of these inductive models and benchmark the results against external data sets.
Then let me introduce the techniques of IGMC and our extensions. In general, IGMC has 3 steps. The first is to process our user item matrix to generate the input, where we include one-hop subgraphs around the target node. The second step is a local node labeling strategy, which allows IGMC to be inductive and thus independent of the original global matrix. Finally, we feed the subgraphs into a GCN architecture consisting of 4 GCN layers, an aggregation layer, and a dense layer for prediction. Now, for our extensions, we mainly improve 2 parts. The first one is to enhance the RGCN layers by adding graph normalization. It basically adds an additional learnable parameter to control the level of the main shift operation, which can help to preserve more structural information of graphs. The results show that graph norm can slightly decrease the test RMA to give better predictions. The second one is to modify the aggregation method on massive parsing layers. The original IGMC model uses symbol concatenation. We further apply max pooling and LSTM attention method. Based on the experiment, using max pooling improved the result most significantly, and it also reduced the training time by abstracting key features in a reduced dimension.
We investigate the efficacy of IGMC and our best 2 performing extension models on a range of datasets under varying conditions. We test against 3 main conditions: the total number of ratings, the number of relations in the data, that is, the number of actual ratings an item can be given between 1 and 5, and the data sparsity of the dataset. We found that the number of ratings generally appears to improve the model performance across the board, while the sparsity of data in the training dataset generally reduces the transfer learning performance of the model. And increasing the number of relations appears to improve its transfer learning metrics. Our extensions to IGMC improve the performance of the model in both the original and transfer learned datasets. IGMC proves to be a viable state-of-the-art approach to inductive recommender systems. Furthermore, we have shown it's possible to extend IGMC to produce stronger models that retain its desired properties. We also discussed benefits in introducing graph normalization and alternate layer aggregation methods. However, our research also shows potential challenges in both the IGMC model and in our extensions. Future work can be definitely done to improve and expand on these aspects. Thank you for listening. Please view our poster and report in the following links.